Hey class, we're back again, and now we're going to start looking at chapter 8.3. So in chapter 8.3, we're focusing on scale diagrams, and the idea here, the learning target, is to understand and use scale diagrams in 2 dimensions. So before we do that, we really have to know a couple of vocabulary terms, because you're going to find this entire chapter really focuses on scale factors, which you can't really understand unless you understand what a scale or scale diagram is. So to the left here we have a scale diagram. But starting off, a scale is simply a ratio of a measurement on a diagram to the corresponding distance measured on the shape or object represented by the diagram. That is a really fancy way of saying it's a rate that compares, for a good example, something drawn compared to the actual real thing. So you can see that we're not going to fit 10 feet on a piece of paper unless it's an exceptionally long piece of paper, but this 10 feet would represent a 10-foot wall in real life. Now, a scale diagram is a drawing in which the measurements are proportionally reduced or enlarged from actual measurements. A scale diagram is similar to the original. So what we're saying here is that this diagram is in direct proportion. So if this is 10 feet, this would represent 9 feet. And these would both be in the same proportion to the actual room that this is modeling. So if you've ever watched the show Mythbusters, they usually start with what they call a small scale experiment, and that's what they're doing, is they're scaling down their experiment, but they're keeping the proportions the same. Now, a scale factor is a number created from the ratio of any 2 corresponding measurements of 2 similar shapes or objects, written as a fraction, decimal, or percent. So what we're saying here is that maybe this 10-foot line on my paper is actually 1/10 of the size that the actual measurement in real life would be. And so that would be telling me that I have a scale factor of 1/10. Now typically for this unit, we're going to represent our scale factor using the variable k. So that's going to become kind of our universal symbol for scale factors. So I think the best thing for us to do is to look at an example. So here we're looking at example 1, which is drawing a 2D scale diagram that requires a reduction. So we have a builder planning to construct a house on a rectangular lot, as shown in this sketch. It says draw a scale diagram of the lot and housing using a scale of 1 meter to 500 meters. So there's a few things here, and it's going to get a little bit difficult to talk about. What you have to understand is that you are looking at this diagram, and you have to pretend like it's not actually on the paper. You have to pretend that this is actually coming from real life. And what you're trying to do is you're trying to represent this on a regular piece of paper. So most pieces of paper are 8.5 by 11. And if you did the conversion, you're going to find out that you can't fit 12 meters on one of those pieces of paper. So they're giving us a scale ratio here. They want 1 meter on a piece of paper to represent 500 meters in real life. Well, my issue with this is that 1 meter is too long to put on a piece of paper. So what we'll do is we'll probably use this rate to kind of size down our measurements that we have here, and they're going to come out to be decimals. And then once they're in decimals, I think what we'll do is we'll convert those decimals to centimeter measurements that are much more tangible as far as we go on a paper. So let's start off with maybe a simple one. Let's start off with the 2 meter distance between the house and the property line. So using my scale here, I can develop a scale factor. And so here we have actual size of 1 meter is going to represent, so it's representing 500 meters. So if I want my scale factor to pare down, then my scale factor is going to be the 1 meter per 500 meters. You'll notice that my units will cancel, and I have a scale factor of 1 over 500. So for me now, I'm going to convert that 2 meter measurement. So I'm taking 2 meters and I'm multiplying it by my scale factor, which is 1/500th. I'll do that with my calculator, and we're going to move everything to decimal representation. So if I do that, I've got 2 multiplied by 1 divided by 500, and that gives me back 0.004. So that would be 0.004 meters. Now, what I'm recommending is that this is an exceptionally small measurement. So what I would think is that we can easily take that meter measurement and convert it to something a little more tangible, such as centimeters. So we'll set up a conversion factor between meters and centimeters. 1 meter is 100 centimeters, which is going to result in moving the decimal places 2 to the right, and all of a sudden we have 0.4 centimeters. And so this obviously we would be able to represent on a piece of paper. So now I'm putting this in as 0.4 centimeters. So I'm just going to continue to do that with the rest of the measurements. So let's maybe take our 12 meter one here. And so we've got 12 meters. And again, I'm going to multiply that by the 1/500th scale factor. And maybe just because I know I'm going to go to centimeters, I'm going to combine in my conversion factor of 1 meter to 100 centimeters. And so if I do that out, I've got 12. And really what's happening is I'm dividing by 500. and then taking that and multiplying by 100, and that gives me 2.4 centimeters. So there's 2.4 centimeters. So there's my 2.4 centimeters. And the idea being that I could actually measure this out on a piece of paper and create a real scale diagram. Now, what's important is when they talked about proportionality, if you look at the proportion, if I was to relate 2 meters to 0.4 centimeters, you'd find it's a 1 to 1/500th ratio. And the thing is that that's going to be consistent between all of these measurements. So that's what they're talking about preserving the proportions. So maybe what we'll do now is we'll get our 9 meter measurement. So we've got 9 meters. Again, I'm multiplying by my scale factor of 1/500th. I'm then multiplying by my conversion factor of 100 centimeters per 1 meter. So I'll do that out, and I get 9 divided by the 500. And then I'm going to multiply that by my 100, and I get 1.8 centimeters. So I've got 1.8 centimeters. Okay. My next measurement is probably this 4.5 meter distance between the property line. So I'm just going to try and squeeze this in, 4.5 meters. And I think you have the hang of what I'm doing right now, but I just want to follow this through to be thorough. So I've got my 1/500th. I've got my conversion factor. When I do that out, 4.5 divided by the 500, multiplied by 100, I get 0.9 centimeters. So this is now 0.9. So sorry, 0.9 centimeters. There's only 2 measurements left. There's our 40 and our 15. So if we do this very quickly, we've got 40 meters, scale factor of 1/500, and 100 centimeters per 1 meter. So if we do that, 40 divided by 500 multiplied by 100 is 8 centimeters. So there's my 40. And you can see how I could draw this on a piece of paper. Again, we're doing this so that we can fit it on a piece of paper, assumingly. So then we'll take our 15 meters, and we're going to multiply by the 1/500th, and then we're going to multiply by 100 centimeters over our 1 meter. So again, 15 divided by 500, multiplied by 100 to convert to centimeters, and that gives me 3 centimeters. And you can see that really once I've figured out my scale factor, creating my scale diagram is not hard at all. And so that's how you would end up using it or drawing a 2D scale diagram that requires a reduction in this case.